Good morning, class. It's 4 o'clock in the morning on Tuesday. It's 7 degrees outside here in beautiful Clinton, Iowa. I wish you were here with me. Okay, we're going to pick up on slide 16 of our control presentation. There we go. Okay, so we're to discussion of the selection of a good pump in order to circulate water through the system. Correct pump, you need a good selection in order to have a well-functioning system. That's pretty obvious. I like a flat pump curve, and the selection should generally be in the area from the center of the curve to the left-hand portion of the curve. As we look over here on where it says proper, you see the dot is the selection point at design, and it's not way over on the left. The pump manufacturer will have some minimum flow that he recommends for any particular pump selection, and you need to certainly be to the right of that, but to the center portion a little bit on the left-hand side is what is suggested. And it's because systems sometimes wind up delivering more flow than you might suspect, and if that's necessary, or the control system opens enough valves, you don't want to fall off the end of the pump curve. Falling off the end of the pump curve is an area of unstable operation that can damage the pump. So we got to be real careful that we have what they call this driftability out to the right, which is at lower heads and higher flows. And so the improper selected curve, the point is very much over to the right-hand side with limited driftability. Also, the steepness of the curve, for any change in flow, the pump will, if it's a reduction in flow, and you're not doing this with speed control. Now, these slides don't really consider speed control, and we'll have another presentation later that will bring that more fully into the discussion. Speed control, the shape of the pump curve is not nearly as important as it is with constant speed pumps, but you need to know both sides of the argument. And so if the curve is steep, for even a small increase or decrease causes a large pressure change in the amount of head that the pump puts into the flow, and that complicates the ability of the controls to operate in a smooth and very precise manner. So we like, for constant speed pumping, we like flat pump curves along with the ability to not fall off the end of the pump curve. So that's what this selection point is talking about. Okay, with a constant speed system, and even with a variable speed system, if we have significant static head, the pump efficiency is just not going to stay the same as we move to different operating points. You want to have a decent pump efficiency, but because it's changing all of the time, it's not such a big issue if it's changing 2, 3, 4 points, and you're modulating plus and minus back and forth as your system controls the amount of flow that's being circulated. So this small variation in efficiency is not considered to be terribly important. What is important is that the pump curve, again, be flat enough, and you see actually 3 pumps here on the figure. The one with the steep curve, it says pump meets design but not the specified range. And so the little dots over in the hatched regions indicate the minimum and maximum flow that is actually expected by the designer. and either one of the other two curves are acceptable, because you can get to the maximum flow and you don't fall off the end of the pump curve on either of those, and the minimum flow point was obviously acceptable, or that pump would not have been selected. And so whichever one of those two curves you're on with a constant speed system, as valves open and shut, you're going to slide back and forth. And, you know, if you shut a valve, you add resistance, and so the system curve gets steeper, and so the operating point shifts to higher head and lower flow. Likewise, if you open a bunch of valves, there's less resistance in the system, and so the system curve relaxes, and you slide out to more flow at slightly lower head. Okay, so two basic methods can be used to accomplish coil output control from the water side. We can vary the temperature of the water at constant flow rate, or we can vary the flow rate at constant temperature. In reality, we can do combinations of this, but when you start learning the control theory, excuse me, you typically just consider one. So let's see, each control method has advantages. It's up to the design engineer to decide which arrangement he's going to select, and a lot of it has to do with a reasonable cost, as we'll see. Establishment of design flow rates is a necessary first step, so you have to do that no matter which of the two control schemes you're going to use, temperature or flow. Okay, the influence of flow rate on system performance is of interest. Okay, this figure is very important, so we'll spend a little bit of time here. So figure below shows the effect of flow variation from the design rate of a heating system designed for a coil drop of only 20 degrees. But it's common to have not huge drops on some of these heating coils. But again, that's up to the designer. But so what we're showing here is we're going to modulate the flow rate on the bottom, and the design flow rate is 20. So that's with the design flow going through there. Of course, at 100% flow, we're going to get 100% of the capacity of the heat transfer. But look what happens if we drop to 50% flow. If you cut the flow in half, you only drop the heat transfer by a little less than 10%, roughly 10%. You still have 90% of the heat being discharged from the coil. Well, that's, yeah. So if you're going to really cut back on the amount of heat transfer of this coil, you're going to have to drastically reduce the amount of water. So if you want to get down to, say, 50% of the heat transfer, you're going to have to go to 10% of the flow. That's a huge action, and still 50% of the heat transfer may be too much, you know, if you just lightly. So this relationship between flow and the percent of heat that's put out by the coil is significant on a coil designed at peak capacity for a 20-degree delta T. And we'll talk more about why that is here on upcoming slides. But you need to look at this and kind of soak this up a little bit before you just run on to the further slides. Okay, so variations in, well, so this is where the slides say what I've already talked through on the last slide, some of it. But so variations from design flow rate down to 50% have a small impact over the heat transfer rate. So what's going to happen, why this is is that if I cut the flow in half, I increase the residence time in the coil significantly. So it might double the amount of time the water's in the coil, and so it has more time to give up heat, and so the leaving coil temperature drops significantly from that initial 20-degree delta T. So let's say we had 180-degree water in at design, 20-degree delta T would be 160 out at full coil flow rate, but at half coil flow rate, we may be 140 out. And so, or 142 or 145 or something like that, and so what that's saying is that extra residence time in the coil, the water gives up additional heat, and the delta T then expands, and we get not that great a reduction in capacity for that first 10, 15, 20% reduction in flow. So interesting. Okay, so flow rate variations must be significant from the design point to make a meaningful change in the heat transfer rate of a 20-degree delta T system. If substantial flow imbalance exists, the core receiving much less than its design flow rate. So this is another issue. If we don't get the system balanced properly, somebody is going to be short on water at the design flow, and it could be that you're operating in the steep part of the curve, which may if you're way low, you're going to be in the steep part of the curve, and then you may have control issues because a very small change in valve position results in a huge change in heat transfer, and so that can cause unstable flow. So that can be a problem. It's amazing that some of these systems work very well at all. So it's not really as hard as some of this may make it look, but still significant amount of information the designer needs to know and understand. Okay, so just a second here, I need a sip of coffee. Okay, I'm back with you. Flow rate variation. So what we see here is the design curves for 3 different delta T coil systems. And so you see as the delta T, the design, this is design delta T, increases, the performance on the curve becomes more linear. And that can be a good thing for controllability. You just have to select the valve characteristics to match the coil characteristics to give you some sort of reasonable overall control curve. But we see that this 60-degree delta T curve, I mean, it's not a straight line, but it's still relatively straight compared to the 20-degree delta T line for sure. Also, chill water systems exhibit relatively linear heat transfer versus flow characteristics. So that's good to note as well. Okay, so heating systems designed on a high temperature drop, low supply temperature flow basis, and chill water systems designed on a high temperature rise and high supply water temp basis are especially critical cases. These types of systems must be designed with care to ensure that design flows in all terminal units in order to obtain that, so that you have the correct design flow rate in order to get good control characteristics. So I guess you got to be careful on all of them, but especially those. Okay, so here's, well, temperature variation control looks. It looks pretty darn good. Nice straight line. The heat transfer ability of a unit's directly related to the temperature difference between the air side and the water side of the unit. So if you got a given air temperature, and if you're keeping your space at a consistent temperature, uh, you would expect your mixed air to be fairly constant in temperature entering a coil. The big variation would be if you have changing amounts of ventilation air, and you can have that. But if the occupancy is pretty stable, then you would expect to have the quantity of ventilation air roughly the same. And so then you would expect the entering air temperature to be relatively the same. And so, that could set up for a very stable operating situation. Variation of water temperature represents an effective and accurate method of heat transfer control. And the last bullet here, we should use it wherever possible, as it offers relatively accurate methods of control. However, we'll see on the next slide, it's typically a little more expensive than flow control, and so it doesn't happen very much. But, as a potential designer, you need to understand the ins and outs of this. And, it depends what an owner is willing to pay for. If an owner is going to actually occupy the building, then he may be willing to pay a little bit more than if it's an investment project where he's going to either rent space, and even rental space, the guy's concerned that the clients are comfortable, but not as much as if he's going to live there. And if it's just an investment to build the building and sell it to other investors, then not so much. He just wanted to get out at low first cost. So that, those are all factors that get considered. Water temperature control is seldom used as a terminal unit control method. Simple valve control of water flow is generally less expensive. So whatever's cheapest oftentimes is what's done. And it can be done acceptably, but it may not be the most accurate method of control. Okay, so we're going to talk a little bit about two-way control valves. Two-way control valves constructed in two basic styles. We can have a single-seated and we can have a double-seated valve. This shows obviously the single-seated valve. And also they can be modulating and two-position. But both of those must be installed with the flow direction opposing the closing action of the valve. And so you see from the inlet side over here, flow is going to come in and it's kind of directed upward against the plunger here, that if this thing is going to, it could be shut off, in which case the plunger is going to close all the way down and seal on this side of the channel. This is really, circular, but it's going to come down on top of it and completely stop the flow. Or if it's a modulating situation, it's going to move down against this, but the action of the actuator is always to push down against the flow. If you turn this around and you came in here, this would be a problem, because you would have the flow up on top of this thing as well as going through. And when it started coming down, it gets closer to closing, you get less flow here, more of, you're slowing it down, you're building pressure, and that pressure can slam the valve shut, which can cause noise, water hammer, and problems in the system. So, these valves, they have a little arrow on them that indicate the direction of the flow. It's really a good idea to install them the right way, not backwards. Okay, here's a double-seated control valve, generally recommended for high differential pressures, if you have those in the system. Flow direction through this valve tends to close one port while opening the other. So as this one moves up and down, you got pressure pushing, down here, but up here. So it tends to smooth out the movement of the valve up and down. So it creates a balanced thrust condition, which enables the valve to close off smoothly without water hammer, regardless of differential pressure. So this is the double-seated control valve. Not recommended where if very tight shutoff is needed. They talk about the expansion of the stem portion between the seats can force one seat open. Its use in heating systems should be checked carefully on the basis of flow heat transfer graph. So, just an extra little point of information here on the double-seated control valve. Okay, let's look for a few minutes at three-way valves. Three-way valves are generally classified as either a mixing valve or a diverting valve. Okay, so the mixing valve, we have two inlets and one outlet. And so we've got an inlet here. So one flow path is up here, the other flow path is here. As this valve comes down, it allows both, these can be two-position or three-position valves, so it depends. If it's a two-position valve, then, this port is obviously closed, and so the only flow going through is from the bottom inlet. If it snaps down in the other position, it would seal off this bottom port, and then flow from the left-hand side would just be passed directly through the valve. Or if it's a modulating valve, it can move up and down and give different portions of this flow versus this flow. On the diverting valve, we have one inlet and two outlets. So they can be used for similar type applications. It's just, how the designer wants to set it up, and we'll have some discussion about that a little bit later. So either it can be used. It's just a question. It's really a question of what side of the coil do you want to put the valve on. In both configuration, the valve shuts off in an opposing direction to the flow pattern, leading to smooth operation. So you don't want to let these things shouldn't slam shut, which is a good thing for sure. Okay, let's check the time here. We'll go another couple of slides on this one. Okay, the installation of a mixing valve and a diverting valve is illustrated below. Both arrangements can vary water flow quantity supplied to a coil. So on the mixing valve side, here's my supply. So it's a heating situation. This is my hot water coming in here based on the position of the valve. Again, it could be two position or modulating, but if it's blocking this port completely and opening this port, then all my flow will go through the coil. If it blocks this port, then obviously all the water would bypass the coil, or then it could be in a 50-50 position, allowing 50% of the flow through the coil and 50% to bypass, and then they would mix in the valve and go on to the return. Similar situation at the diverting valve. It's just the supply goes directly into the valve, which then selects the flow path out of the valve, either through the coil or bypass around the coil, or what fraction of the supply flow would go through the coil, providing heat to the air, and what portion would bypass. And then the mixing point would be over here at this T on the diverting valve. So, not very complicated. Installation of mixing valve and diverting valve related to a boiler. So both valves accomplish the variation of water temperature supplied to the system. So here, this shows the mixing valve is basically downstream of the boiler. So your cold return water comes back. A portion of it goes into the boiler, is heated, comes back out, and then it mixes with the water that bypassed so that you can adjust the temperature of the water going out to the system. So this would be the hot water here. This is your return water. This could be 20 to 40 degrees colder. They mix. Then they all go through the air separator, and then any air liberated rises to the compression tank or in a bladder tank. It would it could go to the bladder tank and then the air elimination valve. And so this shows the diverting valve, which is the valve is before the boiler. Now, so the question is, I guess, where do you want the pressure drop on this? And we'll get into that here in just a second. But either one of these can work effectively. Okay. The relative position of the air separator and the control valve should be noted, as this arrangement allows full system water flow to pass through the air separator. So you got to make sure that all of your flow is put back together. You wouldn't want the air separator on this side of the valve, because then this portion of the return water would not go through the separator, and we could be carrying air back to the system that needs to be separated out. So we definitely want on either the mixing or the diverting valve, make sure all of the flow goes through the air separator. Also, locating the air separator immediately at the pump suction ensures proper pressurization, because this is where the compression tank is hooking into the system at the air separator. So that's the point of no pressure change, and you want that sitting on the suction of the pump. So this is all very good. Note is made, a high pressure control valve should never be placed between the pump suction and the point of air separation, which would be right in here on this one, or right in here. That would be a problem because of the pressure drop, because these valves have significant pressure drop. And so you could get into a cavitation situation from your point of no pressure change. Big control valve pressure drop then can lead you to cavitation. So you don't want to do that. I think I'm going to stop here for right now. I don't want to run these videos too long, so we will pick up here on the next one. Thank you very much for your kind attention, and I'm going to try to get out of this thing. Somehow I have not done this properly. Okay. That's what I want. Stop recording.